Yeah, so homework question 15.36. We've got vitamin C in solution. So vitamin C is a polyprotic acid, which means it can donate more than one proton. And they tell you that we've got two different Ka values. And that's what's unique about acids, is that if it's polyprotic, each acid has a different Ka, right? They don't have the same acidity. So our first Ka is 6.8 times 10 to the minus 5. And our second Ka is 2.7 times 10 to the minus 12. And what makes these calculations like seem intimidating is, oh, okay, I have these two Ka values, but if we look at this second Ka value, this is so much smaller than our first Ka value that essentially the concentration we're going to get from that is not going to change the pH of our solution. Yeah, we can find that concentration, we can add that to our original concentration, but we're going to get the same pH value. So for most polyprotic acids, we can ignore that second ionization and just focus on our largest Ka value. So we give those two Kas, we're going to ignore the second one because it's too small. And then now, right, how much vitamin C do we have in this solution?
It's 13.2 milligrams per 1 milliliter.
So this tells us we've got 13.2 milligrams in 1 milliliter of solution. So we have to find concentration. So 13.2 milligrams, right? We know for every 1,000 milligrams, I've got 1 gram. So I've got 0.0132 grams of vitamin C. I need to find moles, right? I know for 1 mole of vitamin C, the molar mass is 176, right, grams per 1 mole of vitamin C. So I divide that by 176. So 0.0132 divided by 176. And I get 7.5 times 10 to the minus 5 moles of vitamin C. We need concentration. So now we can bring in our volume, right? So concentration moles per liter. I've got 0.001 liters in 1 milliliter. So I'm going to divide by 0.001, and that should take me to 10 to the 2, right? Yeah, 7.5 times 10 to the minus 2 molar vitamin C. All right, so now we can find the pH. We know Ka, we know the concentration, right? So now we're looking at my Ka would look like essentially the conjugate base of vitamin C times hydronium all over the concentration of vitamin C. We know Ka, we know vitamin C concentration, right? This is X, and this is also X, the hydronium. So Ka 6.8 times 10 to the minus 5 equals X times X over 7.5 times 10 to the minus 2. Right? How many times have we seen X squared equals? So I'm going to multiply that by 6.8 times 10 to the minus 5. I get 5.1 times 10 to the minus 6, right? Square root of both sides. And I get X equals 2.258 times 10 to the minus 3. What is X, right? X is my hydronium concentration. So last thing, to find pH. pH equals a negative log of hydronium. So pH equals the negative log of 2.258 times 10 to the minus 3. All right, negative log. Let's see, I get a pH of like 2.65 for that. And
That's right.
excellent. Yeah. So pH of 2.65. Right. So that challenge was, yeah, it looks scary with having two Ka values, but that second Ka value is small enough that we can really ignore that. And if you wanted to, right, if you wanted to solve for that second Ka, you would do it in a very similar way. And you would just see that that value, and then you would just add that hydronium concentration to the original hydronium concentration. And you'd probably end up with the exact same pH because that Ka is so small.
So that's there to like throw you off, basically.
Yeah.